Hello class, it's Mr. Wicklehouse, and today we are talking about graphing rational functions. And before you ask, I don't know why this paper was orange. Somebody put orange paper in the printer, and that's what we got. It'll change color shortly. Okay. So we've got a few little new vocabulary words. I don't know if you've heard them before or not, but these are just some new ideas that we have to think about when we're talking about graphing rational functions. The first one is holes. These are basically holes in the line that makes up your graph, and these are points on our function that do not exist, and it leaves a small gap or hole in the curved line that is the function. We'll give you an example of this a little bit later. Another new idea, which you may have heard before, was an asymptote. There are several types of asymptotes. We have vertical asymptotes, horizontal asymptotes, slant asymptotes. Sometimes these slant asymptotes, people will call them oblique asymptotes as well. A vertical asymptote happens. There are lines that happen when the denominator equals 0. So remember all those excluded values that you guys have been finding? Well, those are vertical asymptotes. And what they do is they create boundaries, if you think of it like a wall, that your function cannot cross. So when you're graphing these things, these lines will not cross through these vertical asymptotes. The next one, horizontal asymptotes, are lines that happen when certain criteria are met between the numerator and the denominator, which create boundaries, but the boundaries can be passed through occasionally. You want to think about them like a wall with a door in it. So the line can kind of pass through it, but the only time it'll pass through it is like when it's really close to the origin. And a lot of times these horizontal asymptotes primarily come into play when we're thinking about our end behavior of our function. Finally, slant asymptotes or oblique asymptotes. They're similar to horizontal asymptotes, but the lines are not horizontal. They're like any other line you could think of, so think y equals mx plus b. Okay. That's our last orange page. So let's go on to something nicer. Okay. Here's what our holes look like. So we've got this function here. Okay. And when I go to graph this function, it looks like a straight line, except I've got this one little hole up here. And where that comes from is if I take this and simplify it. So let's factor the top as we've done a million times. This is x minus 2, x plus 1, and then x minus 2. You guys know that from the work that you've done in this unit that this x minus 2 goes away, and so our function is just this here, this x plus 1, which is where this line comes from. But because of what we've got going on here, that x minus 2, I've got the excluded value x cannot equal 2. So right here at 2, we can see we've got a hole. Now that's what those holes are, and that's where they come from. They're those excluded values. Okay. Now let's talk about vertical asymptotes. So as I've said, vertical asymptotes happen when the denominator is equal to 0. Well, here's our function. Here's a picture of our function. Right here, this dashed line here, which is usually how we represent these things, is our vertical asymptote. In order to find that vertical asymptote, I just take the denominator, 3x plus 12, and I set it equal to 0 because that's what I want to know. Solve it. Subtract 12, divide by 3, I get x equals negative 4. Okay. So my vertical asymptote happens at -4. It's the line x equals -4, which is a vertical line. That's all there is to it. Simplify this, factor it, whatever you end up having to do in this denominator, then set each piece equal to 0, and every place where this denominator is equal to 0, you'll get a vertical asymptote. Now this is different from the wholes, because notice the wholes happened where we canceled out. We got an excluded value here, but they canceled out, where this one here, there was no canceling out. The function where this function here on the denominator equaled 0 was at x equals -4, and that was your vertical asymptote. So that's the difference there. You can have wholes and vertical asymptotes. Okay, horizontal asymptotes. There's 3 rules to horizontal asymptotes that you need to remember. The very first rule is if the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote happens at y equals 0. So right here, at y equals 0, we can see the degree of this one is 0, the degree of this one is 1. That means the denominator's degree is higher than the numerator. So we apply rule number 1, and this horizontal asymptote happens at y equals 0. Those are the easiest ones because you don't have to do any kind of calculations or anything like that at all. Let's look at rule number 2. Rule number 2 states that if the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote happens at where y is equal to the ratio of the leading coefficient of the numerator and the leading coefficient of the denominator. You're probably sitting there saying, "Say what, Mr. Wicklehouse?" Well, look at this example here. So we can see that the degree of this numerator is 1 and the degree of the denominator is 1. So if these degrees match up, all you have to do is look at this ratio right here. So I can see that that ratio is 3 on top, 2 on the bottom, which is, 1.5, or however you want to think about it. If you want to think of it as 3/2, then that's fine. Which means that looking here at my graph, my horizontal asymptote is right here at 1.5. Okay? That's really all there is to that. You just look at the ratio of the leading coefficients. Okay? Alright, last rule. This one isn't too bad either, just a lot to remember. If the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. So there's no work to do here for the horizontal other than, determining if this is greater than that, the degrees are greater. And if they are, no horizontal. You can see if I drew any kind of horizontal here, that line is going to cross it, whatever. Alright. But something else comes into play here. And this is additional to rule number 3. Just because there's not a horizontal asymptote does not mean there is no asymptote at all, beyond the vertical asymptote that we know exists at -2, because, yeah. So I'm calling this rule number 3.1. If the degree of the numerator is 1 more, exactly 1 more than the degree of the denominator, then there is a slant or oblique asymptote. In order to find this, you must you must do long division. Because this could be x cubed, and this could be x to the fourth. If it's one more, you're going to do long division in order to find this slant asymptote. Now, this slant asymptote is just a line, just like the horizontal asymptote, but it's in the form of y equals mx plus b. So let's finish this one up by doing that. So I've got x plus 2 divided into x squared plus x minus 12. Remember, I say, what do I multiply by x to get x squared? Well, that's just x, so I get x squared plus 2x. I'm subtracting that. Goes away. Got negative x left. Bring the negative 12 down. What times x gives me negative x? Well, that's going to be negative 1. It's negative x minus 2. I'm subtracting that. That goes away. I end up getting negative 10 here at the end. In this situation, I do not care about the remainder. Just ignore it. So now I've got this line here, y equals x minus 1. Okay? You just graph this line, come down here to minus 1, then we're just graphing through here, and you can see that this thing is just following through that pattern for this line. And this thing comes down really close here, comes up really close here when I'm graphing it, and that's all there is to it. And that's it. Okay, the rest of it you should be able to figure out. If you have any questions, then come and talk to me. I'll see you later.